I'm just going to wait. So look at your right hand and tell me what each thing did. Yeah. Yeah. Okay. Exactly. So you got a force coming out of the force. The direction of the force is your palm, but it was a product of your current, or your current rather, and your magnetic field. So those two aspects are really, really, really important in that. Now, what was so that was the right hand rule. What was the left hand rule? Same thing, but for an electron. Okay. What you just said is very, very important and contrasts it to what we're doing today. All right, so Sabine said it's for an electron, and I was hoping Cedric would say it's for a proton, right? But that's not necessarily what interests us in electricity, right? What interests us in electricity is current, which is the movement of those things. And what we saw last week was just a proton moving or an electron moving, and it was free to move wherever it wanted. And then if it was in a magnetic field, it would do what kind of motion? Circular, yeah, very good. But today it's not going to be free to do that kind of motion, right? So you're going to have a charge in a wire, right? And if it's in a wire, you can't do really circular motion because it can't just jump out of the wire. Do you know what I'm saying? Right, so he's going to have a force, and it's going to do something, and then we're going to figure out what that is. So that's exactly the name of today's topic, is that magnetic force on current carrying wire. Okay, this is PowerPoint number 24. Could you guys take that up, please? We're skipping over 23. We're going to come back to 23 after, right? So we haven't done that one yet. So magnetic force on a current carrying wire is what we're going to do today. I want to look at this example here. We're going to use our right hand, and we're going to imagine that this wire here on the right is carrying a current, all right? And on the left, the current is turned off, so it's not carrying a current. But as soon as you do carry a current, it flexes to the left and to the right. Check that out. This is an actual physical phenomenon where the wire in an electric field will bow to the left or bow to the right. And how did we figure that out? Well, that's easy. We used the right-hand rule. And we talked about it last week. We said that current is, or sorry, not current, but charge is moving in a certain direction. That's exactly what's happening here, though, right? So in this case, we're saying that the current is passing in this direction, right? And that it's feeling some force, and that's what's making it bow. Now, is this current a flow of positive charges or negative charges? Is what? Negative charges? In reality, it is. But what did we say about the way we draw things? It's when we talk about current, we're talking about what kind of charge? Positive charge, exactly. And even though that's not in reality what's happening, we're saying that when there's a positive charge moving, there's going to be a force if it's in a magnetic field. So let's figure out in which direction. So we're going to use our thumb. All right, so we show our thumb in the direction of the current. We put our palms into the direction of the magnetic field. Sorry, not our palms, but our fingers in the direction of the magnetic field. Which way is the palm pointing? Towards the left, right? So that means the wire is going to feel a force in that direction. We're going to call this, whoops, we're going to call this the magnetic force. Okay? And let's try it the other way around. This time the current's flowing downwards. So we're going to use our thumb to go down, fingers into the board. The palm is pointing in which direction? To the right. Okay, so that means there's going to be a force going towards the right. Just going to wait till my thing loads. There you go. There's going to be a force towards the right. We're going to call this again Fm. But that's all fake, right? Because I told you guys that current isn't actually flowing in the positive direction. Current is actually flowing from the negative side. So then we should actually be doing the reverse of this direction. So it's not that positive charges are flowing this way. It's that negative charges are actually flowing that way, right? So let's use our left hand and see if we got the same result. So we have thumb down, fingers into the board, and the force is still to the left. Okay, so it actually doesn't change anything. Even though our convention is wrong, really, the trick works. Okay? So what we So far, so good? This is not a proton or a charge that's moving in free space. This is a current. And we need to find an expression for force that is a measure of current. So let's go look at this here. We had before that force is equal to, you guys remember what the three things were? You said two of them. QVB, exactly. We said that force is equal to QVB, right? And V, what are the units of V? Meters per second, exactly. What are the units of Q? Coulombs. What are the units of B? Teslas, yeah, they're very good. All right, that's all fine and dandy, but that's not really current. What is current? What are the units for current? Coulombs per second. Now, if you look at this, I could actually manipulate this so that I do get currents per second. Okay? So now I have my current, I, and then M would represent a distance. And through what distance is my charge moving through? The length of the wire, exactly. So this would be, well, you can see it here now, is the length of the wire L. And B stays as B. And so now we have a new expression that kind of means the same thing as what we learned last week, right? But this time it's for current. Same expression. The relationship is still a cross product. You guys still remember that? Yeah. I was just talking to Lee earlier, and he's got some problem for you guys. It's interesting. If the length of the wire goes in the same direction as the magnetic field, what could you tell me about the force? Is what? If the current is going in the same direction as the magnetic field, what could you tell me about the force? Is what? You can say it. Is what? It's opposite. It's nothing. What do you guys think? It's zero, right? Because the cross product of two parallel vectors is zero. Okay, we're going to use that now because this is super important. One of the most important discoveries coming up. All right. Excuse me for my excitement. This is just too cool. Any questions based on this? Yeah. Yes, exactly. It's the part that's in the magnetic field. Yeah, that's a good question. All right. Any questions on this so far? We can move on. We're going to do some examples. I want you guys to use your right hand, or use your left hand if you think it should be negative charges moving, and tell me the force of each of these situations. So I want you to see my right hand here. Can't do this problem without your right hand, so everyone's right hand should be up right now. Is that? You can use your left hand. Sure. So you're trying to find the one where the force is going to be towards the left. In the first example, which direction is it going in? Up. So the force is going up. Let's write that. The second example, which direction is the force going in? Down. Third one? Right? Left. Very good. And the last one. Right. So the answer would be, which one of these is going towards the left? The answer is C. Very good. Yeah, Elizabeth. So remember how when we started circuits, I said that by convention we always start with positive charges as the ones that that's flowing from the positive end of the battery to the negative end of the battery. But in reality, it's the electrons going from the negative end of the battery to the positive end. Whether we use this eye conventionally or realistically is always going to come out to be the same thing. So the direction of this arrow is going to show you where the positive charges go, because that's where the convention is. But if you were to talk about where the electrons are going, you can just use your left hand and it would give us the same thing, right? So if conventionally I is going downwards, that means the electrons are going upwards. Fingers in, left hand, palm is going towards the right. So it gives us the same result as our right hand. Okay. Have a problem for you guys? It's a realistic one? No, not really. It's absolutely not realistic. But it's cool in concept if you think about it, because you can get a force on something by putting it in a magnetic field. Here it says that there is a, I'll give you guys a couple of seconds to read this, and then we'll kind of talk about it a little bit together. So take some time to read it. Okay, so what we have here is a long wire, all right? And long wires exist everywhere on our planet. We have one running under the ocean. That's how much wire we have everywhere. And this wire is going to carry a current, and the current's going to have a certain direction. We have no idea what the direction is. We just know that it runs east to west or west to east. So the point is that it's running perpendicular to the north-south magnetic field. So if this was west and this was east, you'd have a wire that's going from one end to the other, right? And we have a magnetic field from our planet, right? Because this is at the equator and there's a magnetic field there. There's a magnetic field everywhere on the planet. But here we're talking about the equator. And this magnetic field runs in which direction? You guys remember? It's written in there. But the magnetic field of our planet runs from which pole to which pole? Which way? North to south, and geographically it's south to north. All right. So if we're talking about these are our geographic coordinates, right? That means I have a magnetic field pointing northwards. From south to north. So that's my magnetic field. Gravity is in which direction? Where? In, exactly, right? So that was a very good observation. It's not going down in my drawing here, it's going in. So if I were to draw gravity, the force of gravity, it would be, what did it look like? An X or a circle? X. Very good. So it's going in. There's my force of gravity. And if I want to counteract that, if I want my wire to levitate, I need my force to come where? Out, right? So that means that my magnetic force is going to look like this, my Fm. And if my Fm and my Fg, they cancel each other out, what does that mean about this wire? Equilibrium, and that means that what? They're the same. What are you physically going to see there? Like a floating wire. You're actually going to see a floating wire. If your current is high enough, you can actually make it like float up. Doesn't really happen because the current needs to be very, very high. But now we know a lot of information. The force is coming out, the magnetic force is coming out. We have the direction of the magnetic field. So let's figure out first, before we figure out the magnitude, let's figure out first what the direction of the current is. Is the current going east to west, or is the current going west to east? So you have to use your right hand. You know where the force is going. You know where the magnetic field is. So where is our current going? Cedric, what'd you get? What's that? Yeah, absolutely. Okay. So our direction of current I is going to be eastward. Okay? All right, perfect. What is the gravitational force acting on this wire? How do we solve that? I'm not asking for a number, but how do we solve that? Anything gravitational force is? Yeah? Yeah, exactly. So if I have Fg is equal to mass times acceleration, right? That's going to be equal and opposite to my, which force? Magnetic force, which is equal to ILB. We can solve for things, right? So what are we looking for here? It says the current. I need the current to be a certain amount in order for this to flow. So we're going to solve for that. We have m, because it's the mass given to us here. We have g. What's g? 9.8 meters per second squared. Do we have the length? Yeah, we do. Right here, 400 meters in length. Do we have b? Yeah, we also have b. We have 50 Mark Tesla here. So we got everything. We just need to plug it in now. So 100 kilograms, 1,000 kilograms rather, times 9.8 meters per second squared is equal to I, which is what we're solving for, multiplied by 400 meters, multiplied by 5.0 times 10 to the negative 5 Tesla. Let's get an answer. It's gonna be a big number. Yep. Is this puissance 25? Is that right? That might be too high, the puissance. What did you get? 496 000. So I think you're off by a few zeros. 496 000. Units. Amps. So that's a huge current. So the current really does have to be a lot for this to levitate. In reality, we can't get a current that goes this high. Look at, there's a little statement here that says 850 for a big wire, 150 amps is a lot for a big wire. You know at what amperage current starts to become dangerous? 1 amp? 1 amp is pretty dangerous. It all depends on you, right? Because it's your resistance that matters. Remember you guys did that activity and you have to measure your internal resistance? So the lower your resistance is, the more current that's going to run through that. In fact, milliamps could be enough to be lethal. And it's just a matter of where you receive that current. Okay, very good. I want you guys to do this one on your own. It's a very similar example, all right? Different number. Everything is given to you. This time I'm taking gravity out of the equation. You took it, okay, so that's a good question. No, just because only the length of this is given to you. Only the vertical length is given. So you're only going to take this part of the wire. So remember what the battery orientation is and what that means about current direction. Okay? Okay. I should see your right hand. Which way is the current going in? Which way? Down. Okay, so we know our current's going downwards. That should help you a little bit. If the current's going downwards, which way is the force going? To the right. Very good. So current is going down. Force is going towards the right. And now we just have to solve it. F is equal to I times L times V. How did you solve for I? It's the current that determines where the force is. Yeah, that would mean that the current. Oh, no. Right now, so if you're going to give me the magnitude of the force, you can tell me toward the right or the left. It's not going to be negative either way. It's going to be positive. Exactly. All right, so let's see what we got for current. Used Ohm's law for current, which is 15 volts is equal to I times 3 ohms, and therefore I is equal to, what did you guys get? 5 amps, okay. Did you use your calculator for that? Yeah. So 5 amps times the length. Did you convert the length to meters? Good. And did you convert your Tesla, your millitesla to Tesla? Very good. What did you get? 0.025 N? Why not N? Yes, N. Are you making your second guess yourself? To the right. All right, perfect. Any questions on that? Is it clear how I got my current? Yeah, because I'm starting to mesh the idea of circuits and magnetism together. And actually, that's going to be pretty much the norm right now. So we can't forget about circuits yet. We kind of forgot about Gauss's law and stuff before that. Remember those days? And but we can't forget about circuits yet. All right, now here's the pièce de résistance. All right, I have a loop, and this loop has current going through it. Right, so here's my wire that has a current going through it. I can apply this whole force thing on this loop, right? Because look, there is a magnet here, north pole, south pole. There's a magnetic field going from the north to the south. There's a current going upward. So current going up, magnetic field going that way. And therefore, which direction is the force going in? Into the board. Over here, my current is going down, magnetic field there. Which way is the force coming up? Coming up. I kind of gave it away. So the force is coming up, all right? So if there is a force going in here and out here, what kind of motion is this loop going to be doing? Is what? It's going to, sorry, I can't hear you guys. Spin, yeah, it's going to spin. This is going to rotate. And what kind of force is that? When a force makes an object rotate, what is that called? That's centrifugal force. Centrifugal force is what keeps it in rotational motion, but what makes it undergo circular motion? Torque, yeah, absolutely. Torque. And do you guys remember what torque is expressed as? It's what? You gotta remember now from last year. He's not torque. No? Oh, okay. All right, we'll learn it today very briefly. It's very not complicated. It's not very complicated. Who's really, really strong in this class? Hey, you can't volunteer other people. That's like picking up your own hand. All right, Kevin, come. It's easy what I have to ask for you. All I'm asking you for you to do is open the door. So everyone, let's watch Kevin open the door. All right, you're not done opening it. All right, step outside. Okay, bye. All right, come back in, please. No, come back in. Okay, so Kevin, did you find that hard at all? No, okay, not yet. All right, so may I have you try to open the door by pushing right here? Pushing this. Okay, now let go. Come closer to the hinge. Now come even closer. Come closer. No, now you got it. All right, so how do you get more torque? Thank you, Kevin. What's that? You increase the radius, okay? That's the most important part. If your force, the Kevin's force, the more was applied away from the axis of rotation, the more torque he was able to generate. More torque means he was able to open the door easily, more easily. Okay? You guys following so far? All right, so that means there's two variables into how much torque Kevin can generate. Kevin needed to apply force and needed to apply it at a certain distance. Okay, so we need to remember that the symbol for torque is tau. All right, not to be confused with the RC constant. So the torque tau is equal to the force multiplied by the distance. And that distance is the distance from the rotational center. Okay? Distance to the rotational center. Yeah, in meters. Okay? As simple as that. If I increase my force, am I increasing the torque? Yeah. If I increase the distance, am I increasing the torque? Yeah, absolutely. So if I were to push at the very edge of this with all my force, I can easily open the door. If I were to push weakly near the hinge, then I wouldn't be able to open the door. I'm generating no torque at all. Okay. So that's exactly what this is, right? Look at this. It's a force in this direction and a force in this direction. What's the rotational center? There's a little symbol there. Right. So this thing here would be the rotational center. So if I put force there and put force there, this looks kind of like a revolving door, right? Have you guys gone to like Indigo downtown? You know, they have those revolving doors. You push it, you go through. And it's always really awkward if you end up in the little piece with someone else in there and you're walking like a little penguin. That's exactly what this is like, right? And it's rotating in this direction. We're going to define this direction later. We're going to say it's going to be clockwise. And I'm going to ask you a tricky question now, though, so pay attention, please. What is then, according to this, what is the distance of the torque? Is it W? It's W divided by 2. Okay, thank you, Elizabeth. All right. So my torque distance is W divided by 2. So we need to write that. So my torque force is equal to my magnetic force, right? My magnetic force multiplied by the distance from the rotational center, which is W divided by 2. And that's the torque being applied to by what? Is it only one of the forces or both of the forces? And are those two forces helping each other or not? So I have a force going in here, and a force going out there. So are those torques going in the same direction? So imagine this is a revolving door and there's a person pushing in this way and a person pushing this way. Are they helping each other or is it going to jam? They're helping each other, exactly. So these two forces, although they look like they're going in different directions, the torque is going in the same direction. Okay, force is in different direction, torque is in the same direction. Yeah. Magnetic force. So if this torque is helping this torque, then you have to add them together because they're both going, the torques are going in the same direction, right? So that means that my torque in this loop is going to be Fm times W over 2 plus Fm times W over 2. The same magnetic force, because it's the same current, same magnetic field. So then what is my overall torque? What? So FMW over 2 plus FMW over 2 is equal to 2 FMW over 2, which is what? Just FMW. Okay? And this is your overall torque. Okay, so we need to do this a bit more mathematically now, okay? So here's a more defined loop, right? And my loop here is just a square. And this square has a bottom dimension B and a vertical dimension A. Okay, and these are going to be important. We said that the magnetic force, let's say we have this current going downwards on this side of the loop, the current is going downward here. All right. So if this is going downwards, magnetic field is going that way. We can use our right hand to figure out which direction the force is. Which direction is the force? Oh, exactly. And here I have my current, because this is a loop, and the current goes like this. So I have my sun going up and going that way. My force is going in which direction? In. Okay, very good. So here I can draw my force. Ones are all sweaty. Here my forces all coming out. Here my forces are all going in, so I draw them as x's. What's happening here? Am I ignoring this, or is it just not happening, or what's happening? So it's I cross B, right? So if you remember in linear algebra, if you have a vector cross multiplied by a vector in the same direction, what's your cross product? Zero, yes. What about down here? Zero. Okay, so we can actually ignore the top and the bottom part of this. There is no forces being generated on this wire and on this wire because they are parallel to the magnetic field. The current's parallel to the magnetic field, therefore the cross product is zero. Okay. All right, so now we have force coming out here, going in here. We're going to get torque, and that means there's going to be a rotational axis. What's my rotational axis? It's what? Where's my axis of rotation? Which is what? You're going like this. Up to down is right. Up to down in the middle. Huh. Yeah, here we go. There you go. So there's my rotational axis. And this part is coming outward and this part's going inward. So I'm going to say that my rotation is actually kind of in this direction. In this direction. Yeah. I'm just going to erase this FM that I wrote up here. So make sure you're not accidentally putting that. I want to talk about torque. And we said that torque is equal to force times distance. And we solved there that it was, if we go back, the magnetic force multiplied by the width of my loop. All right, so if I look at here, the width of my loop is represented by which letter? B. Okay, so that means that torque is going to be equal to F magnetic multiplied by B. And my torque, my force itself, we learned is equal to ILB. What was the L representing again? The length. And what's the length in this? What letter is my length represented in this loop? A, just A, right? This is my length of my wire. All right, so that means it's going to be that torque is going to be equal to I times A times B times capital B. Right? This is my width, or not my width, my length. Sorry. Oh no, glitching. Okay, I'll come back to it. So A is my length and B is my width. What's length times width? Area, exactly. So in fact, the total equation is going to become that my torque is equal to I times A times B, where this is the area of the loop. Yeah. So remember that torque is equal to, if I go back to my last slide. So if you remember, was the torque is equal to the force times the distance to the center, but because there's two forces acting in the same direction, I just added them up and I got this. Right? So total torque on my loop is the magnetic force multiplied by the total width. And in the new diagram, the width is represented by A or B, sorry, B, not A, B. Okay? So this is pretty big. All right, so we can make a loop turn. What does that represent? We're going to find that out. This works if everything is perpendicular to each other. But throughout this whole process, it's not going to be perpendicular at all times, right? So if I were to look at this diagram here, right, my loop, if we're looking at it from the top, has rotated a little bit, right? So it used to be straight. Now it's rotated a little bit, right? And it's no longer perpendicular, right? Because magnetic field is going in that direction, and now my current is going in this direction here, and therefore they're not perpendicular. So we need to add a variable for angle, all right? And that means that the angle, as it changes, is going to be different. So this is going to be more of a function, okay? So this is going to be important. So torque is equal to IAB sine theta. And this is going to be true until when? At what point? At what point is my loop going to stop rotating? So this is going to go. Right now it's in this direction. It's going to rotate, 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 rotate. This is the next big checkpoint. What's going to happen when my current is perpendicular? There's my magnetic field in this direction. All right. And rotate, rotate, rotate. Here. Actually, this is the current coming towards you, and here's the current going out of you. Right, so here, it's going to go like this. Here's your magnetic field. And which direction is the force going to be at this point here? So this is current I. This is current I. You just have to use your right hand. So thumb coming into you, magnetic field there. Which direction is the force? Up. What about here? Which direction is the force? Down. Are you going to have any torque? There's no more torque. Okay? So that's kind of sucked, right? Because we did this like amazing physical phenomenon where we made a loop turn, and it didn't even make a full turn before it had to stop. Okay, but there's a way to get around that. Okay, so if I were to roll something, did you guys learn at least about angular momentum last year? Yeah? Okay. So angular momentum is exactly what it sounds like. Is when an object is in circular motion, it's going to tend to remain in circular motion. Right, so if I were to rotate something that was first flat like this, it got rotated up until here, and then it tipped the balance a little bit, right? Then it could continue having torque on it. But we need that current to change directions. Okay, so here, this is what I want to figure out. We're almost done, guys. Here's your magnetic field, B. Here's your loop. Here's your point of rotation. What's the force on this direction? Use your right hand, let me know. Say something? Ah. What about the force there? Downward. So it's going to rotate. And let's say it rotates all the way to here. Okay. What's going to be the torque when this loop totally turns around? That means that the point is going to be on this end, and the x is going to be on this end. The magnetic field is going in that direction. This is my axis of rotation. What's going to be my direction of my forces here? Use your right hand again. So this one here is going to be down. And this one here, up. So which way is it going to want to rotate? Backwards. Well, that's annoying because we have a loop that's constantly going to be flipping forward and backwards, right? So what we've actually invented is a device that will, once it passes this tipping point, so we kind of call this a tipping point, once it passes that tipping point, it's going to reverse the direction of the current. Okay, so if you reverse the direction of the current, then this is going to, it's going to be an X here, and it's going to be a dot here because you reverse the direction of the current, and therefore the force is going to continue going in the same direction, and you're going to be able to do a full second part of the loop. And then what's going to happen once it does that again? Reverse it again. And then what's going to happen to this loop? It's going to turn indefinitely, forever. So as long as there's a current in the loop, it's going to turn. That is a motor. An electromagnetic motor, that's exactly how it works. It literally powers any kind of thing. Hydro-Quebec uses this to give the entire, like basically the entire country, electricity. This on this basic principle that if you put a current in a loop, you get rotational motion. Okay? Your fans, your computer fans, same thing. They're all electromagnets. They're all motors. And they work on this principle here. The device that I told you that flips the current is called a commutator, right? And so what happens is when it senses that you're beyond that tipping point that I talked about, the current flips around and it allows the motion to continue. This is like a DC motor. You guys have them in your bins. You guys have a picture of it? Or have it, may I open this? Is there any components for that? Oh, is that an Arduino? This here, what's inside of it, is exactly what I just described. It's a current. It's not doing one loop. In fact, it's doing many loops. And when you have a wire doing many loops, what's that called? A coil. And there's a special scientific term. Starts with an S, you learned it in grade 10. Solenoid, exactly. There's a solenoid in here, which is basically just current that's flowing through in a coil, right? And there's a magnet around it that makes this thing turn. And that's so you provide current through these two plugs here. That makes the current go through the thing and turn the motor inside, and the motor is connected to this thing. Very, very simple. And that's actually how like 89% of or 90% of motors are made using that principle. Here's another image and explanation for that commutator piece. I don't expect you to know exactly how it works because that's more electrical engineering university level, but you should know that you need to have a flip of direction of the current in order to have a continuous circular motion. Okay? Any questions on that? Okay, we reached a good spot for us to take a break. Come back in 10 minutes, and then we're going to do some review problems for the test. Yeah. Yes, the gist of it is anything that's possible. This is not an exam. The last thing we did for the exam was RC circuit. Yeah, so there was no like mass spectroscopy or anything like that. There was not even a magnetic field. Or everything was like there was some stuff that's coming up. Exactly. Yeah, And so there's no right hand, left hand? That's not easy. There's no, that's the best. Yeah. Oh, right. Yeah, sure. Okay, so I have to make it into PDF in a moment. Okay, I'll do that right now. So come back at 2:03, okay? Oh, no, yeah, 2:03. C'était le lab 3, Margot? I sent it to Margot. Directed value is whenever there's a baseline, you have to take into consideration the baseline. Is the trend, or where does your right hand? You call it C. Sure. Be careful what you call it. Actually, did I give it a color? Can I take back the green? You don't want to do like a giant project? Oh, okay. What's the bug? Okay. What is the program doing? Oh, it's kind of like a class, like a house classification. Only looking for YouTube content, right? So the view, the view not finding So I see that you
Oh my God. Simple plan and unexpected journey.
well, this and this, you can understand the time, so it's like, I'm not gonna look at that. Okay, so for review, here's what I want you guys to do. There's 5 review questions. There's an hour and just under an hour and a half left of class. It'll be worth it. So there's 5 review questions. They're on the PowerPoint that I posted on Google. It's called Test Review. Or you can just follow them on my screen, but I think you're going to need to open it up on your own. Once you do, you'll see those 5 questions. What you need to do is with your group, the table you're sitting with, you can put your table if you want. You don't have to do the group that you're with. But I want you guys to answer these in any order that you see more comfortable. There is a great advantage for having to solve as many of these problems as you can in this next 1 hour and a half. I'll be around helping you guys. All right. And but you guys need to, the idea is that you solve as many of these in an hour and a half possible. Now, in the other group, so you guys are second to do, in the other group, the best team was able to do 3 questions in an hour and a half. And you guys can easily do more. Okay? Now here's the perk. For each question that you get, I'll add 1 mark to your test. All right? So you have an hour and a half with your buddies to solve it. Zach, sit down on the board there. Yeah. Any table has any ratio, but when you do that, you need oil on it. Oh,
Non, excuse, 10 plus 5. Wow. Ça donne 2 fois ça la moitié. La séquence, c'est l'expression qui est à 4 secondes S.
C'est quoi ton unité de capacité?
Non, mais je l'ai fait avec mon.
You have to write it. So you have to write 15 times 10 to the
C'est ça, ça donne 2 fois ça la moins 4 S. Et là, pour B, tu vas faire D. C'est D. Tu vas faire B est égal à R fois X. Là, ton B, c'est 30. Ton R, c'est 40. Puis ton I, tu vas le trouver le problème. C'est en parallèle. Puis le jump en parallèle va être pareil. Donc, là, c'est 15 F. OK. J'ai juste dessiné genre le circuit.
Yeah, it should be one of the things.
Non, enlève bien une switch entre les deux. Le C, ça va être 40. Ça va être 32. C'est aucun calcul à faire. Non, c'est pas C. C'est la liste qui change. On est rendu à la liste.
Mais après, tu as la réponse de 10.
La réponse de D, c'est 10. La réponse de C, c'est 30. Parce que, vu qu'il n'y a pas de capacité, parce que c'est x égal à 0, on les enlève. Puis comme c'est en parallèle, le big bloc va être égal à l'intensité.
En 10, tu peux pas.
Est-ce que tu sais quoi?
Non, c'est juste
Le V, ça va être 30. Ça va être 30 à la 2. On va le faire. 201.